Hello, welcome back to JP Academy ETAP MasterClass, where we produce specialists or professionals in power system design, analysis, and protection. In this session, I will be teaching on voltage regulation in an electrical power system. I'll take that again. Voltage regulation in an electrical power system. So the first question is, what is voltage regulation? Voltage regulation simply refers to voltage control. It means ensuring the voltage level is within permissible limits. It means ensuring the voltage level is within prescribed limits. Simply put, we regulate voltage in order to prevent overvoltage or undervoltage, which can damage our equipment. It is important to note that when the voltage level of a power system is operating within prescribed limits, then the efficiency of that system is high. And once the efficiency of a power system is improved, the active and reactive power losses are reduced. Remember, I am teaching on voltage regulation in an electrical power system. Having explained what voltage regulation is all about, we can proceed by establishing a basic understanding of a power system. A power system is a network of electrical components which are interconnected for three major purposes: generation of power, transmission of power, and distribution of power. So here's an interesting question. Why do we need to regulate the voltage level? Usually, electrical energy is generated at the power stations far away from the urban areas where consumers are located. Now, this energy which is generated is delivered to the ultimate consumers through a network of transmission and distribution. Now, I have a detailed teaching on power systems. You can call or send a message to me using the number displayed to request for this teaching, because in this session I won't be dwelling on power systems. I'll be dwelling on voltage regulation, and we are currently on why we need to regulate voltage. For satisfactory operation of motors, lamps, and other loads or equipment, it is desirable that the voltage at the consumer's terminal is maintained substantially constant. A wide variation of voltage, that is when the voltage level is not operating within prescribed limits, may cause erratic operation, may cause an undesirable operation, or even malfunctioning of consumers' appliances. The major factor that generates voltage variation is the variation in load on the supply system. When the load on a supply system is increased, the voltage at the consumer premises falls due to an increase in voltage drop in the alternator synchronous impedance, transmission lines, transformer impedance, feeders, and distributors. The reverse would also happen should the load on the power system fall or drop. What I mean is, an increase in load on the supply system causes a percentage of undervoltage, while a decrease in load on the supply system causes a percentage of overvoltage. Now, you can refer to my teaching on load flow analysis or power flow analysis, where I explained in details how to determine the worst case overvoltage scenario as well as the worst case undervoltage scenario by the use of load variation. I also gave practical illustrations on how to model the loads and power source. So simply refer to that lesson, and if you do not have that lesson, kindly reach out to me by sending a message to the number displayed. So such voltage variations, that is overvoltage or undervoltage, are undesirable, and the supplier is required to maintain the voltage at the consumer's premises within prescribed limits so that the consumer's apparatus or equipment may operate satisfactorily. This is achieved by installing voltage control equipment at suitable places, such as at generating stations, at transformer stations supplying to feeders, and at the feeder's end if the drop, that's the voltage drop, exceeds the permissible limit. Now, it is important to note that the voltage regulating equipment or the voltage control equipment is provided. It can be provided at more than one point in the power system because of extensive transmission and distribution network, as well as different load characteristics of different load circuits in the power system. Having exhaustively explained what voltage regulation is all about and why we need to regulate the voltage, here comes the big question. How do we regulate voltage? How do we control voltage? How do we ensure that the voltage level is within permissible limits or within prescribed limits? Now, the first factor to be taken into consideration is the type of supply system. Basically, we have an AC supply system and we also have the DC supply system. The method for voltage regulation on a DC supply system differs from the method for voltage regulation on an AC supply system. Now, in a DC supply system, we can have two possible scenarios. The first scenario is in a case of feeders of equal lengths fed from the DC supply system. And in order to regulate the voltage or control the voltage in a case of feeders of equal lengths, we use overcompound generators. And the second scenario is in a case of feeders of unequal lengths or feeders of different lengths being fed by one generator. The voltage at the end of each feeder is kept constant by means of a feeder booster or a series wound DC generator. That was for a DC supply system. Now let's move on to an AC supply system. I'll be dwelling more on AC supply system in this series of voltage regulation. In an AC supply system, the voltage level can be controlled or regulated using the following methods. I'm going to be giving 10 methods for voltage regulation in an AC supply system. As I mentioned earlier, a power system is basically made up of the generation domain, the transmission domain, and the distribution domain. So in each of these 10 methods I will be giving you, I will tell you which domains they can be applied. So the first method is the use of excitation systems. And they are used at generating domain. The second method is the use of automatic voltage regulators. They are also used at the generating domain. The third method is the use of tap changing transformers at the sending end and receiving end of transmission lines, in factory substations, in distribution substations, and transmission substations. The fourth method is the use of booster transformers, and these are used in the transmission domain. The fifth method is the use of induction regulators. These are also used in the transmission domain. The sixth method is the use of series capacitors, and these are used in long extra high voltage transmission lines. The seventh method is switching in shunt reactors during light loading or while energizing long extra high voltage lines. The next method is switching in shunt capacitors during high load or low power factor load, and they are installed near the load terminals, in factory substations, in the receiving substations, and in switching substations. The ninth method is the use of static shunt compensation devices, which have shunt capacitors and thyristorized control for stepless control of reactive power and voltage. These static shunt compensator devices are also known as static VAR systems or static VAR compensators, SVS or SVCs. And this method is used in the transmission domain. The 10th method, which is the last for today, is the use of synchronous condensers, and this is used in the distribution domain at the receiving end of a transmission line. So we've come to the end of today's session. In our next session, I'll be teaching on what each of these methods are all about, why we should use each of these methods, where we should use each of these methods, when we should use each of these methods, and most importantly, how we should use each of these methods. I hope this session was helpful and informative. Thank you so much for listening. My name is Jesse, and this is JP Academy. See you in the next session.